Hi, welcome back to CS170 Spring Session. Couple admin things really quick before I get into the next part of Chapter 8. So, apologies, but on Mondays, I had to move my office hours back a little bit due to some personal reasons. So, I'm going 6 to 7 p.m. now. But Fridays are still 4 to 5 p.m. If I have any more updates, I'll let you know. But just note the office hour times. And if you do want to come to office hours, I do suggest to maybe just send me an email, at least maybe a day before or something like that, or even like within a day earlier in the day, just so I know to have my room up and ready waiting for you. And if it happens that there's maybe multiple students that are trying to get in, I'd rather not have people kind of queued up and waiting. Sometimes it might work out well to have multiple students covering the same topic at one time, or other times it may just be better to spread out the time. So I might say, okay, come at this time, and then the next person I tell them to come in like 15 minutes later or something like that. So if you do want to pop in for office hours, that's fine. Just if you can give me a heads up, just send me an email or something. That would be great. Okay, so that's it for the office hours update. Um, and I think I said this before, but do make sure that if you're going to have a conflict with the exam time schedule, I think we've posted the times for the exams coming up. Really do let us know well in advance, right? And if you have like exemption for disability and stuff like that, you do want to provide us that documentation sooner rather than later, because I'm not the one that actually sets those special exemptions. I have to pass it on to Professor Trees. They have to log it, they have to update it, and all that kind of stuff. So the sooner we can get those type of conflicts, do send it in as quickly as possible, so I can send it on down the line. Okay, so make sure you do that. The other thing was, I think people ask me again about when these extra credit questions are due. Try to do it within that week, right? It does help me a lot, so I can group all of my emails together for each topic and see what the response is for that week. Okay, uh, and the last lecture I did provide an extra credit, which is doing some of the binary to decimal or hex conversions. And I just want to kind of show you something. Uh, Interestingly, like some of the students jumped on this work very quickly. So I'll show you this. Um, so this is the table here, right? And I just have to say, like, you know, this is spot on exactly how we want to see the work done to do this, right? So when you do this for the exam, I'm basically going to tell you, like, for the exam, and I think I've said it a number of times, and we spend enough time on it, both from the book perspective, from the lectures perspective, from the recitations perspective. You're pretty much guaranteed you're going to have base conversions. So really get this down pat. If you get down the mechanics of it, whichever way works for you, it's like 3 points for you. If you can get it down, just crank it out. Okay, and so I don't particularly worry too much about showing you the answer. That's not the point. The reason why I give you these extra credits is to help you prepare for the exam. So you do this work, keep it in your notes, and be prepared to answer pretty much the same exact question for the exam. Okay, so here's like the table. You get whatever values in base 10, base 2, or base 16, and you just follow the procedure, right? This is almost like word for word exactly what was on the PowerPoint slide on how to do it with the remainders version way of converting, right, from the base 10 to base 2, right? I mean, this is like totally spot on, right, how it's done. So this person did all this, uh, and you remember what I said before in terms of adding up all of the exponents, right? Um, so if you can try to follow this and just work it out. So if you can't memorize in your head the mechanics of it, just have it like on a piece of paper for reference to say, okay, every time I convert from base 10 to base 2, this is what I need to do. right? I need to take the number, divide it, and take the remainders, and then make sure it falls to the right, okay? So whatever you have to do that, right? And like I said, anytime you go between binary and hex, the way I like to do it is just take the sets of 4s and then do the conversions and mapping it, right? Because there's only 16 characters to map when you're doing hex, okay? Again, talk to your TAs. Your TAs are going to show you a couple of different ways to do these conversions, and you do what you need to do, okay? But I just wanted to show you this because number one, this was like a very early submission, but number two, I think this is just an excellent example of what you should do to do well with this question when you're guaranteed to have this on the exam, right? So do this and you'll be spot on for the exam, okay? All right, I'm not going to belabor that point. I'll let it go. So yeah, just take this out. I thought it was just a great example to share with you. So let's go back to here. And so you remember, if you remember from the last lecture, we were talking about multimedia. I call it digitization, right? But it's multimedia data representation, right? So I see a picture, I see a video, I hear sound. How is that actually stored in the computer, right? It's going to be stored in a series of zeros and ones, okay? So you remember we talked about RGB for the pixels, and again, I'll emphasize it again. When you're looking at this, there will be some problem that we're going to probably ask you about what is black, what is white, right, and what is a calculation of how many different colors depending on how many pixels and whatnot, right? Just like this here, right? So I give you this picture, I'll have something like this many pixels by this many pixels, X by Y, that gives you this many pixels, right? And then converting that 24 bits, you know, how many bits does it take to store this picture? Okay, that'll be another surefire question that you're going to get. So do make sure you understand how to do this. Okay, and you know, you'll get something like this, right? So maybe I'll put all of it on this color or this color or this color, right? So it's only one of them, so it's fairly straightforward. It's either going to be red, green, or blue. Okay, so be sure you understand that. And you know, basically, now that you have the information digitally stored, then you can do all kinds of algorithms to basically do math to affect how this picture is going to be represented. Maybe you want it brighter, right? Again, when you're doing brighter, you're essentially what I will call doing a shift. I spun right through that. Brightness, you're basically shifting everything, right? Maybe you want it brighter, maybe you want it darker, whichever way. You're basically going across the board and you're shifting everything. Contrast is basically how you look at the difference between the light and the dark, right? And you could be increasing or decreasing the difference between that, right? So these two things in bold right here is important to understand. And so essentially you're, instead of doing like where you did the brighter, applying everything uniformly across everything, you're basically going to apply selectively, whether it's on the darker side or on the lighter side, some sort of, the basic thing is to do a shift, just, you know, add something. Then you get into like adding color, and you basically group like the different ranges and then apply some sort of formula or shift to it, right? In this case based on RGB, right? So you remember we talked about this. So in the shadows, the darker stuff, that'll be down here at the bottom. The middle stuff, you know, something like this background here, and the lighter stuff would be like his shirt, okay? And then you apply some sort of formula or shift like this, +5, +8, minus, right? And you get that, okay? And keep in mind, this is very basic, right? Shifting here, that just gives you the idea. Of course, you can apply a more complex formula, presumably to get like a better, more realistic view, right? But this is just to give you an idea of what you can do once you have everything stored in terms of numbers or digital, 0 and 1, okay? So that's for pictures. And later on, we're going to get into videos, but essentially videos is just multiple slices of pictures, right? So it's just adding a third dimension to your pictures, okay? So that's when we're talking about digitization of images. So let me go into sound, okay? So you probably remember from your high school days or middle school days, whatever that is, um, how do we create sound, right? So essentially there's sound waves, right? So there's vibration at a certain frequency that causes the air to create waves, and then that is analog, obviously, because it's like a curve like this. It's not like that. And then that hits your ear and the tiny bones within your ear. That translates it into a signal that your brain will understand as sound. Okay. And so let's take a look at what this means. Okay. So there's the idea of sampling. Okay. Uh, so like here, you're talking about low sampling rate. What does sampling mean? It means um, like I'm talking right now, right? And let's pretend there's something that records, and their sampling is basically like a snapshot at one particular point in time, right? Uh, so if I do a sample, like let's say a low sampling rate, an example would be like, let's say I take a sample every 5 seconds. That's a lot, right? Maybe every second, maybe. So one sample, one snapshot every second, you'll get something like this. And what you'll see is that, uh, like my voice, I'm talking to you, it'll be very choppy because you're only sampling very low, okay? Uh, so to get better resolution, you're going to increase your sampling rate, right? So you can see what does this curve looks like? It looks very sharp and jagged here, right? Then you get into median sampling rate, you can see the curve gets a little bit smoother, and then you get into high sampling rate, and you can see, an even smoother curve, right? So you don't end up with these little gaps where, um, maybe you have to do some interpolation or you have to do some curve fitting or smoothing to try to figure out where the gaps are and what should that sound be, right? If you increase your sampling, you're taking many pictures of it. That's what they mean by increasing the sampling, okay? Uh, Now, the resolution here means like how many bits per sample, right? So you're going like this. This is like up and down here, and what is that value, right? So you don't see like a 0, 1, 2, 3, 4, 5, or whatever on the left hand side for your x-axis, um, but you can imagine if I store it as 1, 2, 3, 4, 5, that gives you a certain resolution. If I store it as like 1.1, 1.2, 1.3, so on and so forth, you can imagine that gives you a finer resolution, right? Um, and so it's the same type of thing, right? You have like how many slices you want to take this way, the more you get, the better curve you get. Well, then you also have this, how many slices across this way, or resolution, how fine do you want to get that to give you a more accurate curve here? Okay, so it's two dimensions. There's x and y. Okay, x and y. Um, and both ways talk about how you increase the information or the sampling to give you a more accurate representation of the sound. Okay? And this leads us to an important thing. You really should try to note this down, remember this, is the idea of the Nyquist rule for sampling. Okay? Uh, so basically it says that, you know, how much, uh, sampling do you need to get to, quote unquote, get an accurate reproduction of the sound. Okay, um, so this is based on human hearing, right? I mean, we're recording stuff for humans. Um, so, like, for most people, the top of the range of what they can hear is 20,000 hertz. Okay, so basically the Nyquist rule says that what's your sampling rate, you have to be twice as high as the highest frequency. So that's why it's 20,000 times 2. Basically, this is 40,000 for your sampling. Okay, so when we record music or whatever vocal type of stuff, it's basically saying for human consumption, this is the sampling rate to give you a fairly accurate sampling size. Okay, um, if you're some other animal and we're recording stuff for them, and they have a higher frequency range for what they can hear, then you have to adjust your Nyquist sampling, right? So you remember, I don't know how many videos it was, we talked about perfect reproduction, right? So of course, you can get the sampling for sound almost going to infinity, right? So how many samples do you need to get to quote unquote get a perfect reproduction? Okay, and you know, and this is of course taking it from analog to a digital format. And you know, yes, you can argue that digital is not 100% full accurate reproduction, even at this 40,000 hertz. But from a human perspective, for what the typical human can hear, then the 40,000 cycles is a good enough reproduction of the analog sound that you're hearing. Okay, right now, obviously, if I'm copying that digital copy, you're getting perfect reproduction, right? So when I store this digitally, now I make another copy of that, you know, that audio clip. It's perfect reproduction at that point, right? But the original uh, digitization of that sound is not actually 100% fully accurate, right? But it's good enough for human consumption. Okay, so just a side note on that. But for our purpose, just remember Nyquist rule and remember 2 times the highest frequency for whoever the user is, typically a human. 2 times 20,000 gives you 40,000 hertz. That's what the Nyquist rule is saying. How many times do you have to sample for a good enough reproduction of that sound? Okay. Now remember, that's the sampling. How many times am I slicing? How many times am I snapping? Right now, the resolution, right? Again, how many bits per sample? So for every sample, every snap that I take, how is that resolution? Can it be very basic? Like, I don't have that much space, right? Maybe I can only store very little bit. Well, then my resolution is not going to be very great. It's going to be pretty bad, actually, right? So this is the idea of bit depth, right? So how many bits are you going to represent with each sample, right? Um, so here we're saying an audio digital representation usually uses about 16 bits, okay? So 16 bits, that's 2 to the 16th. Um, so that's, I think for most uses, that's pretty good resolution. Okay. Um, so as you can see up here, the point says, if you really want to get an accurate sample, you're going to basically almost get to unlimited bits for a sample, right? But again, you have to come back to what is good enough for human consumption, right? 2 to the 16th bits is a lot, and probably good enough for human consumption. Just the same way as the sampling, 40,000 is probably good enough for human consumption. Okay, so remember, samples goes this way, bits is going this way. So basically, how accurate do you want to be? So try to remember those concepts. Okay. So this is a digitization process. Um, yeah, you can kind of understand this part, right? So you have a sound, right? So a sound's analog, right? And the microphone is picking it up. So a microphone is vibrating as the sound comes across, right? And then that is taken to like an analog to digital converter, right? So it takes like this sound wave and slices it up via sampling, right? And using the bit depth to convert it to a digital format, okay? And then it writes it to memory. And then to reverse it, right? Just like a little picture here, right? So you got like the whole sine wave, right? It goes into the microphone. The microphone, vibrates with that sound wave. It converts it into digital format, which is all these zeros and ones. And then going back the other way to play it on a speaker, it just takes this and goes back out the other way. Okay, and from here to here, right? It kind of shows it separately. It's not really separate. This is not a copy of this, but the way it's shown like this, you can say this is a perfect reproduction of this. This is a copy. The way it's drawn here is perfect reproduction. Okay, now in actuality, that's not really what's happening. This is all just one thing. It just kind of comes to here, and then it will get converted into the speaker, right? And the speaker will read the digital into and convert it into analog, right? Digital to analog, and then you get sound waves coming back the other way. Okay. So, well, similar to pictures, well, what do you get when you have your sound digitized? You can have all kinds of effects, right? So you can isolate certain types of sounds and strip them out, right? You can identify them, and mathematically apply like a filter to filter those specific sounds out, or you can add sounds in. Um, so this is very common, I guess, from a music standpoint. This auto tune, right? Um, and something like this, removing the waves that are too high or too low for the humans to hear. Um, so again, that's just kind of saving on space. There's no point in storing some of that information if it's not really going to be heard anyway, right? Um, so you have that. And then we go into images and video, right? So we talked about images before, um, and how the picture is two-dimensional, right? So the X and Y, and that's how we counted the number of pixels and the pixels, how many bits that took up. But if you look at it as video, remember what I was saying, it's basically a series of these pictures, one right after the other, right? So it's just adding another dimension to it, okay? Um, and you could picture, so these slices or pictures are essentially a frame, right? They're calling this a frame. So you call this pixels per frame, okay? Now remember, we did the calculation back earlier here, and we calculated how many of these made up the photo, right? So we had this many bits, okay? And actually, for a typical picture, this is kind of small, right? There's actually not that much, right? Now, but picture, you do stuff on your camera, right? You basically can, not your camera, I should say your phone with the camera. Some of the nicer phones, you're probably gonna be able to get 5, 10, 20, some odd meg per picture, right? Depending on how you set it. Now, picture, that's only for one picture. Now, how many pictures or frames are going to go into a video? Okay, so again, this is actually not that much. We're using kind of like a fairly small number here, 640 by 480, right? But the bit depth is 24 bits, right? And then you have a frame rate of 25 frames per second, right? So in 1 second of video, you're going to get 25 of these frames or pictures, okay? Um, so you remember from earlier, we calculate the pixels per frame, which is the same thing as like, the pixels per picture, right? So the X times Y, so 640 times 480 equals to this. And then how many bits per frame? It's like this, right? So you took that was just one picture, right, or one frame. Now, you're going to take this and you're going to multiply it by 25 for a second. Just 1 second, you're going to have 25 of these frames, right? And you can see just in 1 second, we have a lot already. This is like 184, right? megabits. Okay, and so let's say we do it times 3600 seconds. You're talking about 82 gigs. Okay, so you can see, like, depending on what resolution and whatnot, uh, fairly short order you can get to pretty big size videos, right? And if it's running locally on your computer, that might not be such a huge deal. But when you're trying to maybe send this over wireless, right? Send this over through your phone or something like that, um, very quickly you can chew up a lot of your bandwidth there. Okay, so this is where we get into the idea of like compression. Okay, so important definition or important concept to understand is this idea of lossless and lossy compression. Fix this guy here. Uh, Lossless means whatever your original was, that version you can always get back to that. So I compress to whatever version, I can always go back to the original and I won't lose anything at all. Lossy compression means I've taken some shortcuts and I've compressed it and I can never get back to the original copy that I got, like that level of resolution. Okay, and so this kind of visualizes it better. So what's the difference, right? So other than the fact that it's lossless or lossy, well, so lossless, you get a certain type of compression, but look at for a lossy, you can see the compression. You don't have to know the exact number, but you can see it's much more compressed, right? So if you really, really want to squeeze something down, um, chances are you're gonna maybe sacrifice by going from lossless to lossy compression, right? So you get a bigger compression by going here. There's only so much you can do if you really want to be able to come back to the original image. So this restored image here is pretty much one for one, exactly like the original. Whereas you can see here, if I try to restore it, I'll get something, but it won't be the original. It'll be something less than the original, right? So just understand this idea, lossless versus lossy. Okay, and then these are examples of stuff that are lossless versus lossy. Okay, so let's say zip files, right? JPEGs, MP3. Okay, uh, if you do a search on the internet or whatever, you'll be able to see a whole bunch of other examples, but just at least try to know these examples here. Okay, these are pretty standard um, uh, compressions. So you should be able to know this and understand what's the difference between lossless and lossy. Okay. Wow, I'm already hitting like a half hour here. Yeah, I think I can hit this. Right. So we have the audio compression. Okay, so remember what I said before, taking out the sounds that are too high or too low to hear. So probably not the end of the world, right? So you can hit that with the audio compression. Um, and really sound takes up a lot less space than video. So some of the sound compression that you can do probably is adequate, and you don't have to worry about getting into lossy versus lossless and the trade-offs that you have there. But keep in mind, when I say I'm removing sounds that are too high or too low to hear, it still means that it's not the original sound, right? So I am having a lossy compression, right? Even though I can't tell, I can't hear, it's still lossy compression. So keep that in mind. That's sort of like a little bit of a trick question, right? Um, so remember that on the sound side of things. Now, on the video, you are sacrificing something when you're doing lossy compression, right? Um, you might say, well, okay, humans, when they look at changes in brightness, it's very, uh, you know, um, very easy for people to kind of see that. So you want to be careful when you do stuff that sacrifices on brightness. Um, so you want to try to keep on that. But small changes in color, maybe people are less sensitive to that, right? So you play around with it, but it's a balance, right? You can push it to a certain point where it becomes very noticeable. Um, so when you're making the same type of trade-off that you do on sound, so sound, you're talking about too high or too low to cut those. For video, where you want to play around with is the color side of things. The brightness, not so much. Try to kind of keep that somewhat unchanged or lossless, because humans are pretty sensitive to seeing changes in brightness. Okay, so that's what you're looking at when you look at video and picture compression, where you have to sacrifice something to try to get that smaller size. Okay, all right, very quickly here. So MPEG, so yeah, you can see this, right? You talk about video, YouTube, Netflix. I mean, our lectures are recorded, it's stored there. And they all do some sort of compression, right? YouTube is going to store compressed. They're not going to store like the original version for you. Um, so so MPEG, it's basically storing things from one frame to another frame. Actually, there's probably a lot of things that are exactly the same, right? So it's not like one frame, you go to the next frame, there's so many things like all different, right? So because it's like from one frame to another frame, there's a lot of stuff that could be kind of the same. You can just say from this frame to that frame is exactly the same. Then you can save a lot of space that way. You don't have to store repetitive stuff over and over again. Okay, and you can also see that with when they call run length encoding, which I think I should have it on here. Run length encoding is the same type of thing. Maybe there's a sequence, there's a whole bunch of zeros or a whole bunch of ones, or just some sort of repetitive thing like 0, 1, 0, 0, 1, whatever, right? Those type of things, it stores how many repetitions there are. So instead of storing 10 copies of it, it only tells you there's 10 copies of this thing, right? So that saves a lot of space there, right? So same thing with the MPEG, right? So the difference between one frame to the next, it looks for those things that are the same, and then takes a shortcut and keeps it like that. And so you're only looking at the changes. What you store is actually the changes from one frame to the next frame. Everything else that stays the same doesn't need to get stored. Okay, so that's the idea of MPEG compression. Okay. Okay. So character A, small piece of sound. Okay. Yeah. So it's just talking about like how these different things are represented to if you want to store a character versus a sound versus color, um, so on and so forth. Okay. Okay. So bits being bias free, it's how a bit is a bit, right? It's either 0 or 1, but then how it's interpreted can mean a lot of things, right? Whether you want to, it's part of a sound clip or it's part of a video or whatever. Um, how that's interpreted is essentially this layer on top of that just pulls in all those streams of zeros and ones and then interprets it into a certain way. Okay, so the bits themselves don't know what they are, right? They just know they're either a 0 or a 1. So that's what they mean by being bias free. And so this idea of latency and bandwidth, this is kind of like why we get into things like compression, right? And I'm gonna maybe pick that up in another video after this, but you can see this on the slide here about latency and bandwidth, right? So I look at it as, here's like the size of a pipe, right? It could be a very small pipe, it could be a big pipe, and then it could be like how fast do you go through that pipe, right? How fast does your information flow through that pipe, okay? So that's how I might think of like bandwidth and latency, okay? So you think about how big your pipe is, and then you think about how fast it can go from one end of the pipe to another end of the pipe, right? It could be like a big size pipe, and it could be like information is flowing super fast through it. That's ideally what you like, right? A big monster pipe and super fast information going through that pipe, right? So these are the things you care about when you look at bandwidth and latency, okay? And these are just different checks here, okay? I'm not going to ask you to do this for extra credit. You can take a look at it on your own time. If you have questions about these different checks here, just let me know. This is typically stuff you might look at in preparation for the exam. And here's a repetition of like the teaching objectives or the learning objectives, right? I didn't actually have a particular slide on this run length encoding, but I'll just repeat it again. Run length encoding would be like there's a whole bunch of zeros, a whole bunch of ones, like a whole bunch of repeats, let's say in a picture, right? And you say, instead of saying 0, 0, 0, 0, like 10 zeros, you just say there's 10 zeros, right? And then that's it. So it will be an algorithm to look for all the repeats and compress that into a small size, okay? And then remember, I just spent a bit of time on the videos and how you want to compress on the videos, okay? So, luminance, remember that's change in brightness, change in color, right? Lossless versus lossy. Uh, all of this for the sound digitization. We covered this on the other video about pictures. Okay, so this is chapter 8. All right, I know this lecture ran a little bit longer, but hopefully it covered everything you need to know for this week for chapter 7 and chapter 8. Shoot me an email if you have any questions on any of this material. I'm going to post this up to my resources. Okay, thank you.